delocalizes electron density, and you have one structure where you have not a double bond but single bonds. One point that I hope becomes obvious to everybody is that just about everything that we talk about can be explained based on first principles that we learned largely in Chem 272. Okay, so a lot of the reactivity that we talk about in this chapter is understandable in terms of simple concepts like resonance, electronegativity differences, and so on. And so you don't really need to treat this as something completely new. Try to relate it to what you learned earlier. It becomes, I think, a lot easier to understand. I don't want to dwell on proton or on spectroscopy. Just recognize the thing that we talked about, that aldehydes absorb in a part of the proton NMR spectrum where really nothing else absorbs. And so it's very, very easy from proton NMR to know if you have an aldehyde or some other carbonyl. For the C13 spectrum, recognize also that the carbonyl carbon atom is typically the weakest signal in your spectrum, because remember that in C13, the intensity of the peak correlates with the number of hydrogens attached. And since there are no hydrogens attached, this is usually a very weak peak. It's also downfield. For ketones and aldehydes, it's usually around 200. We need to kind of remind ourselves of the ways we know of preparing aldehydes and ketones. We know quite a few actually right now. And so let's kind of go through these one by one. So if you have an alcohol, of course, you can oxidize it to the carbonyl. If it's a secondary alcohol, it can only undergo oxidation to the ketone. The primary alcohol, on the other hand, then it can oxidize to the aldehyde, but then that oxidation can go one step further in the presence of water and give you a carboxylic acid. And so this oxidation has to be done under anhydrous conditions. Another way we know of making ketones is by the Friedel-Crafts acylation reaction. And then there's some methods that we've talked about in past chapters, which are hydration of alkynes, and also hydroboration oxidation. Okay, so we know that you can take an alkene or an alkyne, do hydroboration, then oxidize the vinyl boron species that you have, and you end up with a aldehyde or with a ketone. And from here, obviously, you just oxidize this. There are ways to go, by the way, there are ways to go directly from here to the ketone, but most you probably do it stepwise. So these are kind of the methods that we've learned. So what this suggests is that when you see a ketone or an aldehyde, you need to mentally kind of think about what is the potential precursor compound. In other words, if I see this ketone, where did it come from? Did it come from oxidation of an aldehyde? Did it come from hydroboration or whatever? So if you do that, then these kinds of transformations, I think, become second nature. Finally, we talked about the fact that ozonolysis and pyrite cleavage of vicinal diols is also a way to generate ketones. Okay, so the reactivity of ketones and aldehydes is really what's occupied us and what will continue to occupy us, really. And remember that there are two basic types of reactivity here. There's not, one is nucleophilic addition to the partial positively charged carbonyl carbon atom. So you end up going from a planar sp2 hybridized carbon atom to an sp3 tetrahedral compound by the addition of a nucleophile. We saw various nucleophiles. We'll go through those momentarily. But this kind of makes sense, right? I mean, you know that this bond is polarized, nucleophile has an electron pair available to bond to an electropositive carbon atom, and so on. And then bases will pull off the alpha proton. Now, of course, this suggests that or requires, I should say, that the carbonyl compound have an alpha proton. So this kind of reactivity, this here, is not something you're going to see with a ketone like this, for example. So if I have if I have a phenyl group here and a tertiary butyl group there, then there's no alpha proton. Here are the two alpha carbons, but they're fully substituted by carbon. No alpha proton, so you're not going to be able to see this kind of reactivity unless you have at least one alpha proton, okay? So just make sure that you recognize that. Now, this proton turns out to be much more acidic than you would otherwise imagine. And the reason is pretty obvious. It's because it's next to a partially positively charged carbon atom. And now the enolate is a very good nucleophile, and it reacts with electrophiles. And so we're going to see this reactivity a lot. But recognize that there are two kinds of reactivity. The carbonyl can act as an electrophile, or the alpha carbon can act as a nucleophile. And this actually creates a lot of complexity. That's a lot of the structural complexity of organic compounds depend on exactly these two kinds of reactions. Okay, so the first kinds of reactions that we looked at were reactions with acid. And since you have non-bonding electron pairs on the carbonyl oxygen atom, it kind of makes sense that those can be donated either to a proton, Bronsted acid, or to a Lewis acid. And when that happens, recognize that the carbonyl gets activated towards nucleophilic attack. In other words, once I transfer that acid, be it a proton or a Lewis acid, now if I write the resonance structures for this species, it's not the same situation here where I have a charged resonance structure. Here, the resonance structure is a cation where I'm pointing. And so that indicates that that's going to be a even more reactive electrophile than before that happens. And so this is one reaction that we're going to see. And then nucleophilic addition usually involves a charged species like this, where Y is typically a metal or proton, and you end up adding XY across the double bond. So it reminds us a little bit of the kinds of additions that we saw to regular old alkenes, right? Not alkenes where one atom is a carbon, the other is an oxygen. And then there's a unique reaction that I alluded to moments ago, which is the oxidation of the aldehyde all the way down to the carboxylic acid, all the way up, I should say, the carboxylic acid. Okay, so these are the kinds of reactions that we see. First of all, let's start with cyanohydrin formation. This, as it turns out, is an important reaction, even though it seems a bit weird. You start out with hydrogen cyanide and base, and cyanide is a good nucleophile, and so it can add to things like ketones and aldehydes and form these stable cyanohydrins. And this is a reaction that positively will not take place with a isolated alkene, a C double bond C. And the reason I think is pretty clear, that the product in such a case would be a carbanion, a very strong base, whereas the product in this case is an alkoxide, a much weaker base. And so you end up getting these cyanohydrin compounds. Now this process is reversible, and you can go from the cyanohydrin back to the ketone. And then we segue from there into a discussion of exactly how this takes place. Recall that the electron pair, in this case from the cyanide, has to find a home. In other words, the electron pair has to exist within some kind of an orbital. The only empty orbital it sees is the anti-bonding pi star, which is empty. And so as this nucleophile approaches the pi star, this carbon atom rehybridizes. It goes from sp2 to sp3. It goes from planar to tetrahedral. And the reaction proceeds until you're at the bonding distance of carbon and carbon. Then we talked about hydrates. Hydrates also turn out to be kind of simple looking, but useful and important in biology, as we indicated. So the mechanism that we talked about for the hydrate formation is sort of the same one that you're going to see for each and every one of these additions that are catalyzed by acid. So in all cases, here's what happens. You end up with a proton transfer step. That activates the carbonyl towards nucleophilic attack. You get attack on the nucleophile, get the tetrahedral intermediate. So it's always the same. Activate, nucleophilic attack. Then proton transfers take place. And then there's your hydrate. So all of these reactions follow exactly that same pattern. And whether the attacking nucleophile is water or methanol or what have you. The next thing we talked about, or the next reaction, were reductions. And we said that this is a reaction that we talked about way back when, actually. And it turns out that you can reduce ketones and aldehydes with hydride. Now, we draw hydride as H minus, but of course you know by now that we don't really have a free H minus. That what we have is a source of a reducing agent that behaves as if it were H minus. And this reaction is irreversible, unlike cyanide addition. The reason it's irreversible is the same reason that we never have free H minus. This is a fantastically strong base. And so for this reaction to reverse, you have to spit out a very strong base, H minus, which is not a good leaving group. Cyanide, on the other hand, is a weak base, and so it's a good leaving group, or reasonably good leaving group. So this is an irreversible reaction. Once you form that nucleophilic addition, it's not going back. Now, the sources of hydride that we've used are sodium borohydride, a reagent that we saw in Chem 272 when we discussed hydroboration or oxymercuration reduction, and lithium aluminum hydride. These are two very common reducing agents. They're by no means the only two. As I told you last week, lots and lots and lots of aluminum and boron and other hydrides that are used in organic chemistry. But arguably, these are the two most common ones. And the reason you need two of them, and that you can't make do with just one or the other, is that borohydride is very selective. It reacts with ketones and aldehydes. It doesn't react with much of anything else. On the other hand, LAH, lithium aluminum hydride, will reduce lots and lots of other functionality. It will reduce acids, esters, amides, nitriles, nitro groups, you name it. And now, in all of these cases, in order for the reduction to take place, the carbonyl group has to be activated. Remember what we said about activation of the carbonyl group? We said that carbonyls have non-bonding electron pairs on oxygen. Those can react with either a proton or with Lewis acid. Once that happens, the carbonyl is even more electrophilic than it would have been. So that happens here. In the case of lithium aluminum hydride, the lithium cation acts as the Lewis acid that activates the carbonyl. And so this carbonyl now is activated towards hydride. It's more reactive than the one without the lithium stuck onto it. Sodium is not nearly as good a Lewis acid as lithium plus, so sodium borohydride actually will not reduce carbonyls unless there's water or methanol present, or ethanol. And so if you take a carbonyl compound, you throw it into PHF or ether and sodium borohydride, not much happens. And the reason is that you need this activation of the carbonyl by hydrogen bonding the solvent before you'll get nucleophilic addition to the carbonyl. Okay, then we talked about Grignard reagents and related compounds, related additions. And recall that the significance of this was that you're forming a new carbon-carbon bond. So this adds to our repertoire of reactions that we are aware of that allow you to form new bonds of carbon. And in both cases, alpha, lithium, Grignard, whatever, additions to the carbonyl, you always do get this activation. So the brommagnesium plus, this stuff here, is a Lewis acid. It engages the electron pair on the carbonyl, activating it towards ethyl addition here, and then you get the red bond. Lithium does much the same thing, and it is the activation step that precedes the nucleophilic addition. But in both cases, you end up with a tertiary alcohol. And we talked also about 1 and 2 carbon homologation reactions. Recall that if I start out with an alkyl bromide of a certain fixed length, I can extend that chain by either one carbon atom or two carbon atoms, just by converting the bromide to the Grignard, then allowing it to react either with formaldehyde, one carbon, or ethylene oxide, two carbons. That gives me the alcohol, which we know how to convert to the bromide, so in net, in both these reactions, you end up extending this chain by one carbon atom, or extending the chain by two carbon atoms, the two being provided, in this case, by ethylene oxide. So this turns out to be something that is useful to do in chemistry. Finally, we talked about the various ways of forming a tertiary alcohol. And I said that any two of the alkyl groups could have been the carbonyl, and then the third one would have been the nucleophile. And so for any tertiary alcohol, where R1, R2, R3 are different, you can have, in essence, three ways of accessing that just by doing a nucleophilic addition to the appropriate ketone. And so you need to be able to see that. It's not hard, really. I mean, if you pick these two alkyls, then obviously this had to be the nucleophile and so on. So this led us to a discussion of protecting groups and the formation of acetals. If you take a ketone or an aldehyde and a primary alcohol, secondary not so much, but primary, or methanol, and acid, you can form these compounds that are called acetals, where you have two oxygens on what used to be the carbonyl. And the mechanism here is exactly the same as ever. Okay, so we're going to go through this mechanism until you're sick of it. And I hope that we can then remember this, because actually this mechanism, as you're going to see, is very similar to the things we're going to talk about in chapter 20. So first step, activation of the carbonyl, nucleophilic attack. That gives you the tetrahedral intermediate. Then you get some proton transfer steps. Then you activate the other oxygen atom. And once activated, you can, so this is just a little bit different. So once activated, then you can form you can form this cation, and then the cation is activated towards the next nucleophilic addition, and then proton transfer gives the final product. So it's essentially the same as hydrate formation, and each of the steps should look completely logical to you, and nothing is really mystifying here. The fact is that it is fairly long. And so you have to remember that it always gets started by activation of the carbonyl. And once you're there, once you remember that the next step is nucleophilic addition, pretty much follows. Now, we talked about hemiacetals also, and we said that there are some compounds that are of interest in biology, sugars in other words, that are stable hemiacetals. So a cyclic hemiacetal of this type is more stable in cyclic form than it is in the acyclic form, and that's certainly true for glucose, and also for the sugars, the 500-ring sugars that form the backbone of RNA and DNA. And so these carbon atoms, this one right here, this one right there, these are considered aldehyde equivalents, okay? So this carbon atom and that one, even though it doesn't look like an aldehyde, actually it is. Okay, so it reacts like an aldehyde. And so if I take, say, D-glucose and I treat it with sodium borohydride, I'll reduce it to I'll reduce this to an alcohol. And so that's what I mean by it's an aldehyde. Now, this led us to a discussion of protecting groups. Remember, I took this as the example. If I want to make this Grignard, I really cannot. This will never form because it will annihilate itself. This carbonyl will react with this nucleophile, not the same molecule, but in a bimolecular reaction. And so what I do is I mask the reactivity of that carbonyl by forming an acetal, then I form the Grignard, do whatever, and then unmask it when I'm ready to. Now, this masking step and the unmasking step have to be done in high yield, or this is just not going to be useful at all. Fortunately, these acetal reactions take place in very good yield. Okay, so nitrogen can also act as a nucleophile towards a carbonyl, once the carbonyl group has been activated. And so for the imine formation, it's the same mechanism. Activate the carbonyl, nucleophilic attack the tetrahedral intermediate. Proton transfers, ejection of water here, proton transfer. So it's always going to be the same. Now, one thing to watch for when we're talking about nitrogen, the reaction is acid catalyzed. That means that you use less than stoichiometric acid. If you have superstoichiometric acid, then what will happen is that the nitrogen atom will be protonated all the time. This is a nucleophile, it has an electron pair. This is not. And so if you've converted all of your amine into ammonium salt, then that first step won't happen because you won't have nucleophile. And so this is a reaction that works really well with, you know, a few mole percent of acid. You add 100 mole percent of acid, and the rate goes essentially to 0. And the reason is because if you completely wiped out that electron pair, you don't have a nucleophile. Now, imines are what you get with primary amines. Now, if you have secondary amine, then you get an ene-amine. Ene-amine because it's an ene, double bond amine, it's an amine. The mechanism is exactly the same. There's nothing different. You get activation of the carbonyl, nucleophilic addition, tetrahedral intermediate, proton transfers, loss of water. Now, the difference here, the only difference is that the proton has to be lost by the alpha carbonate because there's no proton on the nitrogen. And so once you lose this proton, you're at your enamine step. But it's always the same. Activation, nucleophilic addition, proton transfers, and so on. We talked about the reduction, different kind of a reduction of carbonyls. So we're not talking about now reducing this to the alcohol, but reducing it one step further, all the way down to the methylene compound. This can be done with the Wolff-Kishner reduction. That's hydrazine as the reducing agent, base, and heat. This reaction works really well. The mechanism is one that we talked briefly about. It involves formation of a hydrazone first. So in other words, the hydrazine reacts with the carbonyl, and then proton transfers take place to give you this species. This species collapses with loss of nitrogen to give you the reduced compound. And we mentioned that there's an acid-catalyzed version of this reduction. It's called the Clemmensen reduction. The mechanism there is fairly complicated, involving single electron transfer, so we don't need to talk about it. The Wittig reaction is one that we mentioned, which uses this strange reagent called an illite, and it's a very useful reaction in spite of the fact that the triphenylphosphine has to be recycled at the end at some cost. And the reaction is an interesting one. The mechanism here is different from anything we've seen because you get nucleophilic addition of this carbon, negatively charged carbon to carbonyl. Up to there we're good. But then what happens next is that you form this four-membered ring that collapses to give you phosphine oxide and alkene. This looks just a little bit like a metathesis reaction. And in one sense, this is a metathesis, but it is not metal catalyzed. So these oxophosphateins are real. For a long time, nobody believed this was real, but you can get NMR evidence at low temperature. And that pretty much covers what I wanted to review for chapter 18, which is going to be, did I say 18? It's 19. Yeah, 19. Okay, so that pretty much covers what I want to say for chapter 19. Chapter 19 is the last one that we will cover on the exam on Friday. So let me tell you a little bit about the exam. It's going to be pretty much the same kind of drill. There'll be some predict the products questions, there'll be some mechanisms, and there'll be a little bit of spectroscopy, not a lot. And the questions are going to be all of the same type that you've seen up to now, and that you've seen on the first hour exam and on those hour exams that I posted from last year. So I hope nothing is surprising to you. I'll say a few more things maybe on Wednesday, but you know, keep in mind something that I keep telling the class. When it starts to look really complicated, then back away from it and consider that maybe you missed the hint or the easy part. None of these problems are supposed to be killers. It's supposed to be things that you've seen before and that you apply, things that you've learned in the lectures or from the reading. If it looks really hard, then maybe it's not that hard. You just missed the easy part. So let's start chapter 20. Chapter 20 is a chapter on carboxylic acids, and this is more or less more of the same. Okay, this is not. So I shouldn't say more of the same, but it introduces little that is radically different from what we've seen in chapter 19. And so in chapter 19, we saw quite a bit of things that we could relate to earlier work without too much trouble, but that were new for us. It turns out that chapter 20 is going to look really similar to what we saw. So first of all, what's a carboxylic acid? I mean, you already know. I've shown acetic acid here, and this is, I've highlighted the non-bonding electron pairs on oxygen. These are the kinds of acids we're going to be talking about. You remember that we have this other kind of organic acid called a sulfonic acid. Turns out that the sulfonic acids are much stronger acids than the carboxylic acids. Okay, so and this brings up another point that I keep saying. When somebody says this is a strong acid, this is a weak acid, or strong base, or whatever, the question in your mind should be compared to what? Okay, so compared to this acid, this is really a very, very weak acid, like almost 10,000 times weaker. No, 1,000,000 times weaker. So, no, 100,000. Okay, so, but, regardless, in terms of, if you mix these two together, proton transfer will take place very readily from here to there. And so this acts as an acid, and this will act as a base if these two are mixed together. Now, these compounds have been around for a long time. And so there are common names all over the place that we unfortunately need to remember. Fortunately, they're easy to remember. So butyric acid, that comes from Greek meaning bull, okay? And why is that? It also comes from the Greek word meaning butter. So this is the odor and awful taste of rancid butter. And so butyric acid is really lousy, terrible smelling stuff. Caproic acid, that comes from, and caprylic, C6C8. These two come from the Latin name of a goat, caper, upper, C-A-P-E-R. Why is that? Well, because goats, if you've ever been around a goat, you know that they have a distinctive odor. And that's because of these two straight-chain carboxylic acids. Formic acid comes from the Latin word for an ant. And if you've ever crushed ants in your kitchen, and you smell your fingers after that, you'll get a hint of formic acid. Formic acid is fairly toxic, and ants use that as a defense mechanism. So some ants will inject this into you, fire ants, and you end up experiencing a certain amount of pain. We've seen maleic acid and fumaric acid, these are alpha beta unsaturated. And then there are compounds like this where you have two carboxylic acids in the same molecule at the end of the chain. So this is oxalic, malonic, succinic, butyric, adipic, and if I go one more, phenolic. And how did I remember that? Yeah, somebody read. Okay, good. Because it's, oh my, such good apple pie, right? And so anytime yeah, well, I mean, these kind of mnemonic devices work, right? So, I mean, in this case, it's something anybody can remember, but one of the reasons that I asked you to try to relate work that you, or concepts that you learned in this chapter, to stuff you learned way back when, one of the reasons I asked you to do that is because the more connections like that you make, the easier it is to remember stuff. And so if you try to remember facts in isolation, it's very, very difficult to do that. and or anything in isolation. But if you can relate it to something, it becomes much easier. That's why it's so very hard to remember a string, say, of 8 random numbers. That's not easy to do because there's nothing tying them together. When you tie them together with something, it's much easier to remember. Okay, so a little bit about nomenclature. If there are 2 acids, so this was what? Oh my, such good. This was adipic acid. The correct name is pentane dioic acid. Okay, dioic, di meaning 2, and then the oic acid is the suffix for an acid. So this would be hexanoic acid. Fall 4 would be butanoic acid, not butyric acid, but butanoic acid. So butyric acid is the common name. Butanoic acid is the systematic name. Remember, if we had an aldehyde here, it was going to be cyclohexane carboxaldehyde. Here it's cyclohexane carboxylic acid. So you can for the cyclic ones, you can use the same trick. Now, it turns out carboxylic acids are principal groups. And so they have priority over aldehyde, which has priority over ketone, which has priority over alcohol, which has priority over thiol. And so if you have a carboxylic acid and a ketone in the same molecule, then the carboxylic, it's named as a carboxylic acid. So the carboxylic acid gives priority. Not too surprising that you have a double bond, you have a single bond, you got a short bond, you got a long bond, right? I mean, nothing, that's what you'd expect. And so this is, the 2 oxygen atoms are not the same, right? This is the carbonyl oxygen, that's the carboxylate oxygen. Now, it turns out that if you go to the conjugate base, then these 2 bonds, the bonds to the oxygen, are identical. And that's exactly what you would have predicted based on the resonance structure. So you have 2 resonance structures for conjugate base. In one resonance structure, the bond order is 2, and the other resonance structure, the bond order is 1. So on average, you'd expect 1.5 bond order. And in fact, that's pretty much what you see. And so in the conjugate base, these 2 bonds are of identical length. Not so in the carboxylic acid. It turns out that carboxylic acids have boiling points that are quite a bit higher than you would expect. Well, maybe you would expect. They're hydrogen bonded. Okay, so you get strong hydrogen bonding in these, and so they're not as volatile as you might expect given the molecular weight. And in fact, in the vapor phase, these are dimeric. So in the vapor phase, you end up with 2 carboxylic acids forming this 8-membered ring that are hydrogen bonded with the OH engaging the carbonyl oxygen, the one OH engaging carbonyl oxygen of the other. And so if you look at boiling points, vinegar, acetic acid, this is around almost 120. Isopropanol, roughly the same molecular weight, quite a bit lower. Acetone, lower yet, but there's no hydrogen bonding. And then once I end up with isobutylene, this is really overboiling because there's no polar bond and there's no hydrogen bonding, and so that stuff's really volatile. Okay, so I mean, this trend is what you would expect, I think, based on all of our discussions. IR spectroscopy, it turns out that most of the IRs are recorded under conditions where you have this dimer forming, and so the carbonyl is still the major peak in the spectrum, although with the hydroxyl, you also have a strong OH peak in acids. So if you see a carbonyl around 1710, and on top of that you see this broad OH, then that's a pretty good indication that you have a carboxylic acid. Now this seems to be a little bit off because it seems as if you've got it's at a lower frequency than for ketone, right? Because for ketones it was on 1720 or something. And the reason for that is because of electron donation from this electron pair to that carbonyl. So that weakens this bond ever so slightly. We'll see that effect when we talk about reactivity too. So 1710, and you know the typical OH broad absorption. Just as we said for alpha beta unsaturated ketones, here again, because of the resonance effects, you'll see a further lowering of this stretching frequency, sometimes below 1700. So if it's an alpha beta unsaturated acid, then it's a lot easier to stretch that bond because of the resonance effect that we talked about. So no surprises. I mean, it looks, the spectroscopy, it looks pretty much like what we saw for ketones and aldehydes. Not much difference at all. NMR spectroscopy, the OH, no, usually that's way too broad. You hardly ever see that. And that thing is usually spread over so many ppms that you barely see it. The alpha, if you have an alpha methylene, this is in the same range as for a ketone or an aldehyde, so it doesn't help you. If you know it has a carbonyl, or if it might be a ketone, might be an acid, you're not going to be able to tell the difference by proton NMR of the alpha protons. That's not diagnostic. Carbonyl, on the other hand, is diagnostic. In other words, notice that the carbonyl here is at much lower frequency, much lower ppm, low frequency, than for a ketone. And the reason, now this seems a bit screwy, because you think, well, okay, so I have a carbonyl here, it's bonded to two oxygens. The oxygens are electronegative compared to carbon. And so the inductive effect really should be pushing the chemical shift in the opposite direction. That should be de-shielding. But what happens is that you have two electron pairs here, and those electron pairs shield that carbonyl. Remember that the shielding is due to the presence of electrons. And so on the one hand, you have this de-shielding effect from the induction. On the other hand, a shielding effect because of the non-bonding electron pairs. So overall, the carbonyls of acids are around 180. And so yes, these do distinguish carboxylic acids from ketones. Acid-base properties. Well, okay, so here's back to that. We're talking about proton transfer chemistry, and when we say acids, we have to always ask compared to what. So let's take a look at a comparison first and see what we can say. So if I choose acetic acid as the typical carboxylic acid, it's got a pK around 4.7, a little under 5. That's a very weak acid, right? Because if I think about when you think about acids coming into this class from freshman chemistry, you think about sulfuric acid, hydrochloric acid. It's hydrochloric acid, what's the pK? It's negative numbers, right? -6, -7. And so the difference here is well over 10 million. And so this is a huge, huge difference. So I mean, compared to HCl, this really isn't an acid at all. We said that phenols are acidic. Well, phenols are even less acidic. Look, this has a pK of 10, and it's an even weaker acid than acetic acid. We said that ethanol, the OH, is acidic, but this is an even weaker acid, right? I mean, so when we say that this is acidic, we're comparing it to a very strong base, something like sodium hydride. So compared to sodium hydride, just about anything is going to be acidic, because H- hydride is such a strong base. But compared to a strong acid like HCl, this isn't a strong acid. I mean, you've got 20 powers of 10 difference. On the other hand, look at what happens. Compare acetic acid with trifluoroacetic acid. pK here is down at almost to 0, right? So here, this is looking like a very much stronger acid than that. In fact, this is over 10,000 times stronger. And the reason is, of course, the fluorines are stabilizing the conjugate base, something we've seen in the past. So the 3 fluorine atoms, electron withdrawing, will stabilize the carboxylate of the trifluoroacetic acid. So this is actually a moderately strong acid. And so back to what we said. When we talk about acid strength, base strength, always compared to what? Okay? So why are carboxylic acids acidic at all? Well, because the conjugate base is resonance stabilized, that's why. So when we talk about acids, or relative strengths of acids, then always what we need to look at are the stabilities of the conjugate bases. The stabilities of the conjugate bases can be determined either through resonance or through inductive effects, or sometimes through a mixture of the two, which is the case, for example, for this one. Here you have a resonance effect that stabilizes the conjugate base, but also the inductive effect, right? And so, so the way you determine the relative strengths of acids is to look at the relative stabilities of the conjugate bases. Now you say that, well, you know, why is that? Why can you do that? Here's why. Think of it this way. Let's say that I have an acid, you know, A1 and A2, two acids, right? And this is going to dissociate the A1 conjugate base plus a proton. And this is going to dissociate the A2 conjugate base plus a proton. Well, look, the proton is the same. So there's no question of stability of the proton. It's the same species. So what will determine the position of this the relative position of this equilibrium are the relative stabilities of the conjugate bases. And that's why I'm allowed to look at the conjugate bases. Now, in contrast to carboxylic acids, that other class of organic acids that we've encountered, sulfonic acids, are actually pretty strong, right? I mean, these, so the difference here is approaching 6, it's approaching 1,000,000. So if you call this 5 and this minus 1, then the difference in pKa's is roughly 6 powers of 10. So these are actually acids that are more or less in the same league, if you will, as the mineral acids that we've seen before. Now, one thing that you will read very often is that carboxylic acids are soluble in base, aqueous base. And what is really meant by that is that the conjugate base, the carboxylate, is soluble in base. And so, so usually, unless this R group is methyl or or hydrogen, methyl, ethyl, butyl, no good. In those cases, these are going to be water soluble. And actually, you knew that, right? Because vinegar, for R is CH3, vinegar dissolves in water in all proportions, right? So, but once you start making that chain longer and longer and longer, then the whole molecule looks less and less like a carboxylic acid and more like a hydrocarbon. And so hydrocarbons don't dissolve in water. But if you pull off the proton here with a strong base, like hydroxide, then you make the sodium carboxylate, this salt. This is much more soluble than the parent acid. The reason is because this is now a charge of salt, and water can solvate the negative component of the salt and the positive one, right? If you go back to the chapter on solubility from Chem 272, you can convince yourselves why this should be much more water soluble than that. Now, what kind of base do you need? Well, it turns out you don't need hydroxide. You can usually do this with bicarb. So bicarbonate is a very weak base, right? I mean, you can wash your skin with bicarb and you don't end up getting burns like you do with lye. And so it's a very mild base, pH around 8.5. That's basic enough to completely go from, to push this equilibrium all the way to the right. And so how do we know that? And so let's, well, first of all, let's define what we mean by all the way to the right. Okay, so, if I have Avogadro's number of molecules here, there's one left there, then I think everybody would agree that, well, 10 to the 23rd to 1, yeah, it's complete. But, for a practical purpose, if it's about 100 to 1, 1,000 to 1, that's pretty much complete. If there's 1% or less of this stuff, we're going to say that's a complete reaction, right? I mean, just for practical purposes. And so let's just say 100 to 1. That means that you have to, that if I look at the Ka, right, that's the equilibrium that gives me the acid strength. If I look at the Ka, that's this stuff. Then I can divide by the proton on both sides. So just divide both sides by H3O plus concentration. And then take a log of each side. So I take a log of this, that's log of this stuff, minus log of that. Now, minus log of H3O plus is what? That's pH, right? Because the negative logarithm of hydrogen ion concentration is defined as pH. And this is minus pKa. So pH minus pKa is equal to this stuff. pH is this, and this is, because this has a plus, that's minus pKa. So pH minus pKa is the log of the ratio that we want, right? The ratio that we want is 100 to 1. And if this is 100 to 1, then that's 100. Log of 100 is what? 2. Okay? Same as here. So pH minus pKa is going to be log of carboxylate over this. It's a complete reaction, then this ratio is 100 to 1. Log of 100 is what? 2. So all you need is for this to be greater than or equal to 2. And since the pKa of the carboxylic acid is roughly 5, then, let's say 7 to 8 suffices to completely deprotonate the acid. And so that's why bicarbonate can do it. So if you're in the lab and you want to extract a carboxylic acid out of a organic solvent, all you have to do is dissolve the carboxylic acid in ether, wash the ether with bicarbonate, and then your carboxylate is going to end up in the water. And so you can separate very easily using just a separatory funnel carboxylic acids from neutral species and from amines. Okay, so carboxylic acids are basic too. So I think you just told us they're acidic, they're basic. Well, yeah, because for the same reason that ketones and aldehydes are basic, that you have non-bonding electron pairs on the oxygen, and that these can engage either a proton or a Lewis acid. I've shown proton here. Now, this is a very weak base, because this is a very strong acid. So this is an acid that's almost as strong as HCl, which means that is one heck of a weak base. But you can form, with strong acids, you can form this conjugate acid of the carboxylic acid. Now, one thing I want to point out right away, I showed that protonation takes place on this oxygen atom. I didn't show the lone pairs here. These have lone pairs too, don't they? So why is it that the acid, the proton in this case, why is it that the acid is shown bonded to the carbonyl oxygen atom, and the acid is not shown bonded to the carboxylate oxygen atom? They're both oxygens. They have the same electronegativity, but one of
Wouldn't the water one leave? Wouldn't water one leave? H3?
well, this water here is part of the equilibrium. I mean, I left that off, but there's water there. So this. So why here and not there? Yeah, because if I protonate on the carbonyl oxygen, the conjugate acid is resonance stabilized. If I protonate here, it's not. Simple. Okay, now, one last little thing. In the old days, how did they make soap? Yeah, they took it. Okay, so the first thing you got was wood ash. Okay? So you burn wood, you got the ashes. And then you mix that with something that doesn't sound like good starting material for something that's going to make it clean. You mix it with grease. Now, what's going on? Well, the wood ash is a good source of potassium carbonate. And the grease is a good source of fatty acids, like stearic acid. And so we'll talk about that on Wednesday.